Hello, ladies and gentlemen. Welcome. I am Martina Fantini. I will chair the webinar of today on reducing industrial carbon emissions. This webinar was organized by three Horizon 2020 project with the support of the Horizon Results Booster. With the support of the expert, we first formed the project group. And then we started together working on the writing of a policy brief document and in the organization of this event. Just a few words on the projects, on the three projects before going into the main contents of the webinar. So Clinker project granted in 2017 is coordinated by LEAP, Laboratory of Energy and Environment Piacenza. In particular, I take care of this project, and the goal is advancing the integrated calcium looping technology for CO2 capture in cement plant. The cement plant selected for the demonstration is the Buzzi Unicem cement plant located in Vernasca in northern Italy, close to Milan. Buzzi Unicem is one of the 13 partners that work together in a robust work package structure to realize all the goals and the outcomes of the project. Of course, the main one is the demonstration in the cement plant. So you can see the pilot erected in the pre-heating tower and now in the campaign experiment activities. We have also a dedicated work package for transport and storage that will be the object of the presentation of today. We have then realized that is coordinated by Inna Kim from Sintef. This project is developing a way to capture up to 90% of the CO2 from multiple sources in operating refineries at a cost that is 30% lower than existing capture methods. The project includes the evaluation of the CCUS chain, taking advantages from the fact that the consortium partners, some of the consortium partners are in common with the transport and storage projects like Northern Light and Cork CCS. As you can see, the consortium, the project is driven by a strong industrial consortium covering the complete technology value chain. The main goal is to demonstrate the cost reduction in on-site operating refinery center cluster at Cork in Ireland by using a novel low energy solvent, cheaper construction materials and optimal integration with the available heat source. Let's go to the third project, C4U, that is coordinated by Aaron Megeref from the University College of London. C4U spans demonstration of two highly efficient solid-based capture technologies for optimal integration into iron and steam plant, aiming at capturing up to 94% of the total emissions. The project details also consideration on safety, environmental, society, business aspects that are needed for a successful incorporation into the North Sea Project CCUS industrial cluster in Belgium. Let's go now to the presentations. I leave the floor to Alla Shogenova, that is leading Work Package 7 on transport and storage in Clinker project. Alla, the floor is yours.
Thank you very much. I'm a senior researcher from Tallinn University of Technology, and I will present today North Italian CCUS scenario for the cement industry made by Clinker project with partners by Buzzi Unicem and Dow cemented cement plants and Martina Mariani from our master student from two universities. In work package 7 on CO2 transport, use and storage, we have had different objectives. And one of the objectives is modeling of local and regional CCS scenarios. And the local scenario, which include Buzi Unicem, Buzi Vernasca cement plant in Italy, I will demonstrate you now. In our scenario, we first collected data about cement plants, storage sites, pipelines, mineral carbonation studied samples. So 3 cement plants included in the study, in addition to Vernasca cement plant, where we have pilot on calcium looping technology for cement industry. Also Buzi Unicem Robilante cement plant included, and Heidelberg Cement, Italcementi Kalushka Diada cement plant included. They are located in the northern Italy. At yellow boxes, you can see the CO2 emissions in 2020. So from 500 to more than 780 kilotons they produce. And the data, okay, the geological data which we have for the storage site, which is a Malosa structure, we used 18 old wells. The data was collected from public VDP Italian database, but we don't have seismic data. And this Malosa structure located in the low-risk seismic zone 3. So this data from 18 wells were collected and interpreted. And at this slide, you can see this data from these wells and geological information about storage site. So our storage reservoir is Messian Sirgana gravel conglomerate formation located at the depth about 1 kilometer, 200 meters. Average thickness in this structure about more than 80 meters. And composition is polygenic conglomerates with some interbeds of sand and clay. And average porosity of reservoir is 26% and permeability 400 millidar-C. And cap rocks are represented by some terno clay formation. Average thickness 400 meters in this structure, and composition is clays with quartzitic sand interlays. So we, using data from these 18 wells, we composed the 2D and 3D geological models using Petrel software, populated the models with porosity data. So you can see this 2-dimensional model of Stopos Sirgana formation, so 3D model of the reservoir, 2-dimensional model of thickness of Sirgana gravel formation, and 3D model of Sirgana gravel reservoir populated with porosity data. At this slide, you can see all data, geological and technical data, which we have used for estimation of storage capacity. So we used minimum, maximum, and average porosity to estimate minimum, maximum, and average storage capacities. For optimistic storage capacity, we used storage efficiency 10%, and for conservative storage capacity, 4% storage efficiency factor. So we got average conservative storage capacity about 10 million tons and about 25 million tons average optimistic storage capacity. It is static estimates made using Petrel software. Considering that limited storage capacity of the Sirgana gravel reservoir in Malosa structure, we need to determine the most suitable economic case for CCS scenario, which includes Vernasca cement plants. So we estimated that if we take all 3 cement plants, so the optimistic storage capacity will be enough for about 13 years. If we take two-plant scenario, then scenario could be for more than 20 years. And if we take only one plant in scenario, then the storage capacity will be enough for more than 30 years, 33, 50, and enough also for every separate cement plant. But if scenario is only for one plant, it is less economic because for one plant is not possible to share any exploration, transport, and storage and monitoring costs. So the decision was taken to make a CCS scenario for two plants. And in this case, one plant is located Italcementi cement plant located at 34 kilometers from the storage site, and Buzivernazka Unicem plant is located at 125 kilometers from the cement plant. So in this scenario, we made a scenario for 20 years. During the project duration, more than 20 million tons CO2 will be avoided. We estimated total cost for CO2 transport and geological storage, including monitoring. We plan 2 injection and 2 monitoring wells. The most expensive part of the monitoring scenario is 3D seismic survey. And the total transport and monitoring cost will be more than about 50 euro for the Vernazka cement plant located at the distance 125 kilometers, and about 4 euro per ton CO2 for Italcementi Kalushka Diada located at the 34 kilometers. So our conclusions: close location of cement plant to storage site permits to avoid additional compression, which depends on distance, CO2 flow, and starting pressure at the capture plant. Such cost-effective scenario was estimated for Italcementi Kalushka Diada cement plant, located at 34 kilometers from Malosa storage site. The total cost for the CCS scenario will depend on the final cost of calcium looping CO2 capture at Vernazka at the end of clinker project. At the present time, the cost at the reference calcium looping capture cost is 58 euro per ton CO2 avoided, estimated and published by Dilena in 2019, but it could be cheaper for clinker project at Vernazka pilot. So the maximum total CCS cost for Vernazka with the transport and storage in Malosa site for 1 ton CO2 avoided will be about 73 euro, and feasible for CO2 price in EU ETS of about 75 euro. For more economic scenario for Vernazka cement plant, it is recommended to use depleted gas field owned by ENI company in Corte Maggiore field, located only 30 kilometers from Vernazka. However, if calcium looping capture cost could be reached about 40 euro per ton CO2 avoided, then the storage is made at the nearest field, then CCS scenario for Vernazka could be feasible at the price of EU ETS of about 45 euro per ton CO2, or even less if supported for CO2 use. This is reference use for this study, and thank you very much for support for European Commission supporting this project. Thank you very much for attention.
Thanks. Thanks, Alla, to you for the interesting presentation. Let's go now to the Sergei Martinov presentation from C4U Projects. He is a senior research fellow at the University College of London. Sergei, the floor is yours. Thanks.
Right, yes. Good morning, everybody. Good afternoon. Thank you very much for the introduction, Martina. I'm sharing my slides now. So I'm Sergei Martinov from University College London. I'm senior research associate working on the C4U project and leading the work package 4 on the integration of capture technologies in industrial clusters. We are in the second year of the project, and in this presentation I will be talking about some objectives that we have for the studies. We have methodologies that we are developing and some interesting preliminary findings. So steel industry is very intensive in terms of CO2 emissions, and specific emissions are around 1.6 ton of CO2 per ton of steel produced. It is really very challenging to decarbonize, given that steel industry rely on coal, and several CO2 intensity reduction pathways have been suggested for European steel industries, as indicated here in this diagram. And to get on the deep reduction path, as indicated here by the red lines, we need to use advanced capture technologies, such as those that we are developing in the project, so that we could achieve this deep reduction by say 2050, as indicated here, in next 30 years. Capture capture of CO2 from steel industries is not trivial, given the complexity of the processes in steel plants and several effluent gases which are rich with CO2, but also carry other impurities, and these include typically basic oxygen furnace gas, blast furnace gas, coke oven gas. The compositions are really quite complex and would require using different approaches to capture. Can you see the probably, well, this part is, yeah, is that better now, I guess. The fraction of various effluent streams are indicated here, with the major contribution of the blast furnace gas. In the C4U project, we are aiming to implement and to develop these two technologies, called Displace and CASA, which are solvent-based capture technologies, targeting 90% of the CO2 emissions from integrated steel plants. And our preliminary comparison of the key performance indicators against, well, the reference capture technology, which is liquid sorption MDA technology, shows that we could get a reduction in the specific energy consumption by about 2 times, and we can expect a significant decrease in the CO2 avoidance cost from around 50 euro per ton of CO2 to around 40 euro per ton of CO2. Apart from looking at the advanced capture technologies, performance and cost reductions, we are also examining the implementation and technical economics of these capture technologies integrated at an industrial cluster level. And here we examine the impact of impurities on the various parts of CCS chain, including transport, storage, and utilization. We look at the capture and cost penalties for the cluster, and we are also performing the environmental assessment of the technologies at the cluster level. So this is the work that we are doing. And one of the important things is the impact of impurities on the CCS chain, and we know that these impurities, if some of them may be detrimental for the transport, storage, and utilization for various reasons, as indicated here. And the major objective for us is to find a good balance between the specifications for impurities for various parts of the chain to come up with the economic solutions, and to come up with the economic solutions, and make sure that there is a fair implementation for the of the technologies in a cluster if we have several emitters producing CO2 streams of various purities. We have done some preliminary analysis of the impurities that may be present in the CO2 streams captured from blast furnace gas in the produced by steel plants. And here is a table showing the summary with the concentration of these typical impurities in the streams captured using pressure swing adsorption and MEA technology. And by comparing these figures with what with the specifications for CO2 transport and storage set up by the European transport and storage operators, we can see that there are some problematic impurities that require special attention. And in order to meet the specifications here, we would require using either additional purification steps or go for alternative transport, storage, and utilization solutions. So this work was presented in the Trondheim TCCS conference earlier this year. In order to demonstrate the technology's implementation at the cluster level, we are performing case studies, and these are based on the North Sea Port Industrial Cluster, which is located at the border between Belgium and the Netherlands, near the city of Ghent, where our partner is located, ArcelorMittal steel plant. The overall emissions from a number of industries, which are around 500 industries in the region, are about 21 megaton per year. And for the CO2 storage, we are considering transport of CO2 to the off the coast of Netherlands to P18 gas fields, and also look at the opportunities for CO2 transport to more distant formations in the North Sea. We also look at the regional connections of the North Sea port cluster with the clusters around the port of Antwerp and port of Rotterdam in Netherlands. And we are aware of certain challenges that the CO2 transport and storage infrastructure development will be facing in this region, and our review of literature will has helped to identify these challenges, and 3 of these are listed here. So the first one is related to the fact that the offshore infrastructure that may become available for from the natural gas production for storage of CO2 may become available too early for the uptake of CCS, and may require conservation for a certain period of time at an extra cost. The other thing is the other challenge is related to the onshore gas pipeline infrastructure. And again, if this is this would be repurposed for the CO2 transport, it may not become available till the very end of the natural gas production. And the third challenge is related to the implementation of decarbonization scenarios. And here, if we are talking about simultaneous implementation of various decarbonization measures, including CCS and transition to renewable energies, then in the short term, we may see potential surge in demand for transport of various streams, including natural gas, hydrogen, and CO2. And that would require development of extensive pipeline infrastructure that would require significant investments, but later indicates part of that infrastructure may become redundant, and therefore, as there will be decline in the need for transport of CO2 and natural gas. So therefore, some clever optimization and of planning of the phase development of this infrastructure is really needed. So in the project, we are working together with other partners. Some of them are indicated here, including the University of Sheffield, BGR, ArcelorMittal, Element Energy in the UK, and Radboud University. We are performing the techno-economic assessment, environmental and business impact for of the large-scale CCS processes in the region, and we are developing and testing methodologies for the advanced societal to assess the societal readiness for CCS projects and advance the societal readiness of CCS. Thank you very much for your attention, and I'm open to your questions.
Thanks, Sergi. You went a bit longer, but it was so interesting that it was a pity to interrupt you. Anyway, thanks for the slides, and thanks to Alla that I see that she's answering already in the chat, so we can save a few times at the end and dedicating a bit more to the presentation. So now I give the floor to Padraig Fleming from Realize project. He is leading the work package 3 of Realize. So Padraig, the floor is yours.
Fortunately, I don't seem to see him. Maybe he's been disconnected.
Oh, he got maybe a connection problem that he was mentioned at the beginning. So if it's not a problem, maybe we can anticipate the presentation of Milan Elkerbaut from C4U. If you can maybe share your screen, Milan, and give the presentation now, and we will leave a time afterward for Padraig. Sorry for the inconvenience, but
no problem. I'm just starting them now. I hope you can see them now. So I just, actually convenient to follow right from Sergei's presentation. I want to discuss a little bit the policy dimension, also in a wider context from the C4U project. So the whole CCS value chain, and then specifically applied to steel. But as we have seen, it might also very well be relevant for other energy-intensive industries. And last summer, the European Commission came out with a very extensive package, Fit for 55. And there are quite some proposals in there that will affect the business case, the policy framework for CCS and for industrial decarbonization. One of them is the ETS itself, which will have much more scarcity in a much quicker time frame, so potentially by 2040 already. But on the other hand, there's also a lot more innovation funding that might be made available through the auctions of certain allowances. Then the carbon border adjustment mechanism is a way to deal with carbon leakage risk, and this is important if we want private companies themselves to invest in transformational technologies such as CCS. There are a number of other proposals, communications, etc., also forthcoming over the next few months. I think this will also really have an impact on the debate on CCUS in Europe. Next month, there will be a sustainable carbon cycles communication. This will go into both things like natural based carbon dioxide removal through afforestation, but also really the technological side and regular emissions reductions, such as what C4U is trying to achieve in the steel sector. There will also be a carbon dioxide removal certification mechanism next year. The reason why this is important is because some of the ways in which you can actually achieve carbon dioxide removal would also make use of CCUS infrastructure, particularly the transport and storage infrastructure. And you also might have hybrids, such as when bioenergy is involved. And then there are a lot more economy-wide almost initiatives on recovery funding, much more generous state aid. And there are various industrial strategies, also one for hydrogen. While that is an alternative to CCUS, it might nevertheless be important for the development because not all hydrogen will be delivered through electrolysis, and hence blue hydrogen also, again, using CCS might be relevant. So this is a bit a wider picture. Then my colleagues at UCL and Climate Strategies have also worked on this policy brief where they have a few very specific recommendations on CCUS, which I want to go through now. First is the importance of the political framework, and specifically to raise awareness also at a much more regional and national level on the importance of CCS deployment. And then there are some quite technical rules on the transportation of CO2 across borders. There has been some progress in that in the London Protocol, but full ratification would really help with clarity and also giving a signal that this is really going to be part of the European industrial decarbonization landscape, etc. Then, while we're on the topic of definitions, I think we saw in the earlier presentation on the cement CCS project also that there can be very specific conditions in for different storage sites. And here, one of the messages of the policy brief is also that we should be looking much more at Southern Europe. If we look now at where CCUS is emerging a bit and where the investment is taking place, there's a lot happening in and around the North Sea. That's great news. But ultimately, for many sectors, it will not be feasible to transport the CO2 across half or entire continent. So we need this in Southern Europe as well, potentially also Southeast Europe. And any clarity on where and what the acceptable storage sites are, what that volume are, perhaps also conditions for what type of CO2 composition can work there would really help with planning and also further investment. So one of the concepts here that is very important in the policy debate is the cross-chain risk. We have these different stages of carbon capture, transport and storage, and all of them need to move in unison. And if one of them has doubts about the other, then you might get stuck somewhere. So the value chain approach here will be very important. So then a practical roadmap will be equally important. This includes perhaps a bit of political consensus or consensus in different member states that CCUS is part of the toolbox. There's also a public and societal dimension here. Some countries are much more skeptical about the use of the technology. Arguably, that should not be the case, although it is understandable, perhaps, given the history of CCS over the past decades. But it is a very important technology. The storage can also be permanent, and the more authorities are convinced of this, the better. When we talk about policies that would support the investment and business case, I think it's also important to cast a pretty wide net. There are policies that are not really directly CCS policies that will nevertheless really have an impact on the business case for low carbon production methods or products. And that can be very important to justify investments in CCUS. So one example would be labels for green materials or other industrial goods, where there really is transparency and clarity on the embedded carbon contents. This is also important if you think about the concept of green public procurement, where government spending would need to be greened over time. And again, I would like to emphasize the linkages to negative emissions. Those will be needed in the EU anyway. That is very clear from the long-term strategy of the EU, and some of these will use CCS as well. So that strengthens the case for CCS. Finally, fair competition and access will be very important. This is not just to mitigate carbon leakage risks, but also there needs to be a level playing field once low carbon production starts to emerge, and they then will need to compete with the more carbon intensive incumbents. The question of technology neutrality is then a very important one for policymakers, especially when you have very targeted financial incentives. It is important that they will be available, not just for a few hand-picked technologies, but a wide range, including CCS, that are compatible with the climate neutrality objectives. A few specific examples also of where this might arise are carbon contracts for differences. This is essentially a policy that would provide subsidies, but based on what is already being provided by the ETS carbon price. So if the ETS price is higher, the subsidy can be lower, and vice versa. Then there's also the concept of important projects of common European interest, which is a way to coordinate a large amount of state aid, usually in multiple member states. And you can either apply these to specific technology groups, like will be done with hydrogen, but you can also envision that it's focused on a region or on a sector, like specific energy intensive ones. And this can also then really support CCS deployment if CCS is considered to play a major role in the decarbonization roadmap. A few final points, also going back to some of the points raised by Sergey already. There are sometimes concerns about lack of available storage. But if we look at the cumulative storage capacity of depleted gas fields, it is already large enough for considerable amount of CCS. At the same time, I would add that the fact that a storage site is theoretically available does not mean that it is available in practice. So hence, this coordination is very important. This is also alluded to a bit with the point on offshore infrastructure being available too early, and then it raises the cost, because who is going to operate a site without the CO2 flowing in? Another issue arises with the onshore gas pipeline infrastructure, because it might still be used for conventional energy systems, so we shouldn't bank on that. And as such, other forms of CO2 transport, not just thinking about extensive pipeline networks, will be needed. So with that, I'll hand back over to you, Martina. Thank you very much, and looking forward to the discussion.
Thanks to you, Milan. Really thanks for this insight into EU climate policy. As written in the chat, you can find this document and download it from Zenodo community. There is a link in the chat. So now Padraig is back. I can leave the floor to the leader of Work Package 3 of Realize project for a presentation of the previous session, but with delay. Padraig, the floor is yours.
Thank you very much. As you can see, I had a little technological meltdown here, which can only happen when you're in the middle of a presentation, apparently. So my name is Padraig Fleming. I work with Airvia, and I'm leading Work Package 3 in the Realize project. Airvia is one of 17 companies involved in the Realize project. I guess maybe to start off, in terms of setting the context, the cost of CCS is reducing. If we take, for example, the Boundary Dam project in Canada, which came into operation in around 2015, the cost was over $100 per ton, whereas 3 years later, the Petronova project had a reduced cost of $65 per ton. A number of facilities which are expected to be in operation by 2024 to 2028 are anticipated to deliver at $43 a ton, and with new technologies, it's expected that will reduce further to $33 a ton in around the end of 2020s. The Realize project itself, I'll just be giving a quick overview today. We have 7 work packages, 4 or 5 of which I will touch on today and give you a little bit more details. Starting with work package 1, which is probably the headline event really, because we're looking at solvent optimization, validation and management strategies. And as Martina referred to in the introduction to the Realize project, we're focused on reducing the overall cost of carbon capture by about 30%. And this is in terms of focusing on the energy consumption, degradation, and reducing corrosion effects of the solvents in the capture and in the subsequent CO2 that is processed. Work package 2 also has 2 other features in it, which I think are worth mentioning. We are looking at the development or the use of plastics in carbon capture and storage, and also the development of non-linear model predictive controller, which is anticipated to be used in optimizing the capture operation itself. Work package 2 is really focused on the demonstration, and on the left-hand side of the picture here, we have a mini pilot plant, which is, as we speak, is just in the final stages of being certified and getting ready for installation in the Irvine Oil Refinery in Cork. So we're expecting that this will be commissioned and operational early in the new year and shall be delivering data for us in the coming year. The picture on the right-hand side is that of the Centef Tiller plant, which is obviously a much larger plant. But the combined effect of the tiller work and the TNO mini plant, which will be installed in Irvine, is that we hope to move the TRL level from TRL level 5 to TRL level 7 in terms of the solution, the amine solution that's being developed. Work package 3 is looking at the business case, which focuses on Ireland, and we look at 2 scenarios: export of CO2 and indigenous storage of CO2. In relation to the indigenous storage, we have a depleted natural gas field in Kinsale Head gas field. It's approximately 50 kilometers off the southwest shore of Ireland, from just 50 kilometers from the Cork city area. It is currently being decommissioned as a gas field, or as a natural gas field, and it has the potential for reuse. It's got a capacity of estimated at 300 million tons of CO2 storage. And on the right-hand side, the focus of the cluster study was predominantly these 3 of the large emitters in the Cork area. So at the top of the picture is the Ada power plant, which is owned by ESB, who are also involved in this research. In the center, Irvine Oil Refinery, also involved in the Realize project. And lastly, the Whitegate power plant at the bottom right of the picture, which is right adjacent to the oil refinery. And that is owned by Bord Gáis Energy, who are also participating in this study. Overall, the cluster is anticipated to produce 2.5 million tons per annum. And the studies that we've done are based on 90% capture rate. However, there are aspects of the Realize project where we are looking at the economics of higher capture rates than 90%. We've also completed, as part of the cluster study, a cost-benefit study. And I guess maybe I won't go into all the figures here, but a few that are worth pointing out. At the very top, there's a power island cost, and this is the cost of replacing the 2 existing power plants and refitting them. So the cost that we're showing here includes that. But the other key issue is the indigenous field development is about 20% less expensive over a 25-year period than the export option, where we would be exporting from Cork by ship to the Northern Lights project. It's also important to keep note of, or take note of the fact that the OPEX cost is the significant cost in terms of carbon capture. And even here, with the 2 power plants being refurbished included, depending on which scenario we look at, it's approximately a fifth to 1/3 the cost overall. Another key element of the cost benefit study is, and if I just take, for example, the base case indigenous table here on the right-hand side, We've got figures here which show that the cost of electricity production with carbon capture and injecting the carbon into the indigenous field is about €76.50 per megawatt hour, and a levelized cost of abatement of €84.10 per ton. And I guess for me, I come from the energy background. Those costs are relatively competitive and are actually cheaper than some of the renewable technologies that are that will be developed in the near future here in Ireland. A further work package is Work Package 4, which is looking at public acceptance, which has a strong focus on education and public engagement, best practice, social acceptability of CCS. And then we have a number of public outreach activities, as well as having an industry club and an advisory board as part of the Realise project. We also have mission innovation countries involved with 2 companies from China and 1 from South Korea, also developing business cases based on the information and knowledge that we're gaining from the Realise project. So lastly, I would say, if any of you have any further queries or follow on after this, certainly visit our website, but also feel free to contact Ina Kim, who is our project coordinator, or myself, or anybody on the project. I'm sure we'll be happy to help. Thank you. I'll stop there, Martina. That's okay.
Thanks a lot, Patrick. We go now to the last part of the webinar, that is the pitch for the from the 3 projects. Then I think we will have just time for a couple of questions. So maybe just start to write it in the chat so we can promptly answer to them. I would start with the first pitch from Clinker, made by Professor Stefano Consonni. The floor is yours.
Okay, thank you, Martina. Can you hear me?
Yes, we can hear you.
Okay, I'm sorry, but I cannot get my video camera to work. You were talking about the technological meltdown. I don't know exactly what happened, but something similar. So please excuse my being present only by voice. What can I say about the Clinker project in just 1 minute? I could start by saying that maybe not everyone knows that about 6–7% of total man-made CO2 emissions come from the cement industry. And therefore, the cement industry is an important item on any agenda to limit the carbon emissions. Our Clinker project aims at demonstrating a technology that can capture about 90% of the CO2 emitted by a cement plant, providing a flow of CO2 that can be either used directly or safely stored in a safe storage for an indefinite length of time. In addition to removing this CO2, there is an interesting economic return in doing this, which is the economic resources which are freed, are connected to the CO2 allowances, ensuring from climate change policies that would be freed after the capture of CO2. And so there is quite an interest in going in this direction. And with the experience that we are gaining in our project, we feel we are in a very good position to bring the technology from pilot scale to full-scale industrial application, which is definitely the next step that we envisage at the end of the experimental campaigns that we have planned. From the point of view of actions, in addition to actions on the technological and technical side, I think what is most important is to keep in mind actions that we need on the policy and legislative side. It is important to create a favorable environment that can make CCS possible. And this is another direction that we must pursue forcefully in parallel to the effort that we are making on the development of the technology.
Thanks a lot. Thanks a lot. Shall we follow the order, the previous order of projects? So I leave the floor to Milan for his speech. I leave the floor to Padraig for his speech. Now,
Okay.
Milan, we don't hear you, so
No.
I switch to Padraig, and then we
That's
come back
fine.
to you. Sorry.
Thank you, Martina. Yeah, well, I think from an Airvia perspective in particular, we see ourselves really as a gas transportation company going forward. So we don't see ourselves necessarily as the ultimate sponsor of a carbon capture project in Ireland, but we are absolutely happy to share all the information we have interested in developing CCS either in industry or developing the indigenous carbon storage site in Ireland. CCS definitely has potential. I think the studies we have undertaken are showing that economically it is starting to appear much more economic now. And I think based on the next of a kind costs, it will be quite promising technology. And I think lastly, I think the important thing to remember with CCS is we don't necessarily see it as being around forever and a day, but it is critical in terms of a just transition and having reasonable costs incurred by industries in transiting to net zero. And I think that's a very important piece. I would echo Stefano's comments in relation to the policy agenda. There's certainly more work to be done there at European level and at state level across Europe to accommodate more technologies, including CCS. Thanks, Martina.
Thanks a lot. So I see Milan back. I leave the floor to you for your pitch, please.
Yes, apologies. There was a network issue from my side and I couldn't hear anymore. So C4U, yes, I think the key thing about the project is that it really brings together not just the technical and engineering side, but also a lot of social science research on public acceptance, on business models, on the social science. And I think it's in this combination of the two that the strength of the project really lies. So anyone that has also an interest in what it really means to implement carbon capture at an actual facility and what the implications are for the other parts of the CCS value chain, what type of policies you need for that, please get in touch for that. We have work packages covering all of these issues, and we'd be delighted to talk about it with anyone, and hope to stay in touch with many of you. So thank you.
Thanks a lot, Milan. We have one question from the coordinator of C4U. The question is to Alla Shogenova. He asks, could you please tell me if you have taken into account of the CO2 impurities on the storage capability given the risk of geochemical interaction and CO2 mobility? Alla, if you can reply to this, please.
Yes, I have already wrote the answer, but the answer is that we did not take into consideration impurities when we calculated storage capacity, because we expect that CO2 will be captured. It will be high level purity. It will be high purity concentrated CO2 without significant admixtures. And we made experiments for Baltic rocks on CO2 rock interaction, but we made experiments of pure CO2 reaction with concentrated CO2. So the impurities were not taken into account. We considered there is no significant real impurities.
I might add to that, Martina, in relation to the REALIZE study. We have used the specification for Northern Lights, which sets, it's quite a rigorous standard in relation to the level of impurities. Now, interestingly, in the power plants, because they're gas power plants, maybe the impurities issues is less challenging. We did have to factor in conditioning for water, NOx, and oxygen levels, but most of the other impurity levels were coming from the capture plant are anticipated to be below the level of or within the standard of the Northern Lights spec. There are other specifications out there which are not as rigorous as the Northern Lights spec, but certainly in our costings we have included that in what we've looked at.
Thanks. Thanks to both. Are there additional questions? Otherwise, maybe.
I don't see any more questions.
Well, there is one actually to Patrick. How do you see reusing the natural gas infrastructure for transport of hydrogen and CO2 in the future decarbonization scenario involving CCS and the transition to renewable energy sources? You're mute.
That is quite a big question. We're looking at the adoption or the modification of gas networks. It's not part of Realize, although the cost benefit model that we have developed for the Realize project can also accommodate, for example, the production of blue hydrogen. So we can adjust the model to say, for example, instead of feeding a power plant, we can actually feed the production of blue hydrogen, which subsequently could be fed into a hydrogen power plant. In relation to the gas networks, I guess gas networks and hydrogen from an Irish perspective is back to the future, because probably 30, 40 years ago, we used what we call town gas, which had, I think, somewhere around 30% hydrogen in it. So I think we see the gas networks modifying over time, although it's very early stages. Hope my sound is okay here. We're going to examine the conversion of the gas networks to blended gas, and then the adoption of islanded hydrogen until we get to a point where possibly there is full hydrogen networks. Also, in the Irish network, our distribution system, gas network system, is relatively new, and about 80% of the components are actually hydrogen ready. But there's the other 20%, obviously, that would have to be modified. The transmission system is a slightly different prospect, and I think further studies have to be done in relation to that as to how it will accommodate hydrogen and what is the timescale for accommodating hydrogen. But CCS, it's interesting in terms of looking at hydrogen and CCS. There are some complementary aspects and some where they will be maybe competing with each other. And I think CCS is probably the early adopter, with hydrogen coming in more so at the back end of that process. But one thing is clear. Last year, we produced 44% of our electricity from renewable sources. And this is creating a lot of fluctuation in the system. But we will need some thermal plant on the electricity system. And we're getting a lot of electric cars and electric heating in Ireland. So I think in the future, we are going to need some thermal plant, but we will need a lot more renewables. We're anticipating a significant increase in renewables onshore, in renewables offshore. But I think the question then is, will some of those renewables in the future be producing hydrogen or electricity? There's a big question over that we haven't answered yet. I hope that answers the question. Thank you.
I think so. Thanks for the detailed reply. I think it's time to close. I really would like to thank this wonderful project group. It was really a pleasure to work with you all together, and a special thanks, of course, to our experts from the Horizon Results Booster, Rob and Federico. Really thanks for your precious support for our activities, and also to help us in keeping the deadlines to complete the work on time. The webinar is recorded, so you can have a look at it in a second moment when it's more comfortable for you. There will be a link in the website of our projects, and well, if you have questions that coming in a second time, you are always welcome to write to us, and we will try to answer to your doubts. Thanks a lot. Have a nice day.
Goodbye to everyone.
Yeah.
Goodbye.
Goodbye. Thanks, Martina.
Bye-bye.
Thanks.
Bye.
Bye-bye.
Bye. Bye. Bye.